Hey guys, welcome to our first video on solving rate problems. From our website, we're going to talk about the idea that we're going to take rate problems, which is basically taking the derivative with respect to a measurement, or it's going to be a rate problem with respect to a moment in time. So let's grab our lesson here, and let's highlight a few things that we kind of have going on. So our first problem we're going to solve is about the spherical balloon being inflated. And I've taken the liberty to kind of go through and highlight a few things and write some notes down here so we can just kind of talk about it. Number one, the volume is changing as the radius changes. So back in the old days, volume's changing, radius is changing, delta V, delta R. Because we're doing calculus, we want to talk about the instant in time, so it's dV, dr. So in other words, we're talking about taking the derivative with respect to radius with respect to r. So we know we've got a volume formula. Volume equals 4/3 pi r cubed. And normally when we start a problem, we want to make sure that the number of variables we have in our function or in our formula always matches the number of rates in the problem. This one's a little bit different because you see two variables. You see volume v and you see radius r. But because we're talking about respect to radius, when you take the derivative of r cubed with respect to r, that only becomes 3r squared. It doesn't turn into a rate. So it's not like implicit differentiation where the variables are different. So when we go to solve our problem, we always want to be aware that do the variables match the number of rates? And in this case, we're going to have one variable that's going to give us one rate, dV dr. And before we even try and solve the problem, we have to make sure that we actually put rates into the problem. If you were to put your radius of 15 into the problem before you put the rates in, all you're solving for is volume. You're not solving for a rate of change of volume. So we're going to repeat those key things over and over and over as we solve our rate problems. Match the variables to the number of rates, put the rates in before you actually try and solve for the moment in time. So once you get to the point where you've got a function, now we're just taking some derivatives. We're going to apply the product rule, chain rule, quotient rule, whatever it is that we have to do to solve our problems. 4/3 pi it's constant, so we don't have to take anything in regarding 4/3 pi. We're just going to take the derivative of r cubed, 3r squared. Derivative of volume is dV dr. Simplifying, and now we've got our rate. We've got how is the volume changing as the radius changes at any moment in time is going to be with respect to 4 pi r squared. So put our moment of time in, which is 15. Do the math, and we get 900 pi. Volume is centimeters cubed. Radius is centimeters. And we don't simplify that to centimeters squared because that would mean we're solving for an area. Our problem is how is the volume changing when the radius is 15? And the volume is changing at a rate of 900 pi centimeters cubed per centimeter as the volume is growing. So that's our first example.